To the club. Get rid of this stuff, little statistics there. So contour plots, basically two-dimensional renderings of a cross-section of a three-dimensional graph. All right, so you can read the blurb, but basically a contour plot is talking about different curves that are created by cross-sections, horizontal cross-sections. And when I say horizontal, it's kind of tricky, but when we're talking about horizontal, we're talking about planes that are parallel to the XY plane. All right, so if we are to slice through a surface with a plane in the form of z equals some constant, so parallel to the XY plane, then that intersection would create a curve. It would create a two-dimensional curve. The collection of those two-dimensional curves is what's known as a contour map or a contour plot. Each one of those curves, each one of those individual curves is a level curve. Right? We call it a level curve because it's a curve associated with a particular level, as in, like, if you're getting in an elevator and you want to get to the third level or the third floor, it's a movement off of the XY plane. Right? So what I did is, a long time ago, I created a Geogebra for this. It's actually so long ago that I don't even know where I put it. So I'm just gonna kind of hope that I can find it quickly. Let me just open my Geogebra, just straightup.org. Let me sign in, probably my Google. Be under profile. Whenever you save something, if you've been playing around with Geogebra and creating graphs and you're wondering where your stuff is, it's always under profile. Right? So some of them I share, some of them I don't. Let's see if I can find it quickly. You could see I kind of went a little nuts over a long period of time. Because the thing about Geogebra is, as indicated by its title, the geo and the gebra, it allows for not just the geometry, but also algebra, right? So and it also does statistics too. So you get so much with this, and there's so many different applications that things go a little, they can get a little haywire. Right? I had hoped that I would be able to find it immediately. And of course, no. I actually have more. It might be in a different account. Oh, level curve. It's right in front of my face. It's like, hey, dude, find your face. Okay, now that you found it, it's right in front of it. Right. So anyway, I'll share this one. I'll put this up on Blackboard at some point. I just got to remember to do it. In fact, you know how that goes. I'll take that as a typo. So just a reminder to create the link on Blackboard so you have access to this. But it's a level curve Geogebra that I created dependent on some function f of x, y, some level associated with a parallel plane with the xy plane that I call a g of xy equals c. Right? And so I established that c is the constant based off of this slider. You could see here that not only is the slider moving and affecting the value of c, but it's also moving the plane. And that plane has certain intersections with the surface. And as it intersects with the surface at different levels, I have this set up to create a two-dimensional graph associated with those level curves. Right? So what I'm getting is a contour plot. Right? So if I animate this, for example, going up and down, up and down, up and down, you can see that it's plotting a variety of different level curves, creating that contour plot. right? So it's kind of cool just to give you the animation. This is slicing through, creating the curves, and what we get, and it's kind of a pretty cool relationship, is the distance between the level curves for certain values of C give us a sense of the slope. Okay, so and that would be consistent with the slope of the three-dimensional figure, right? But as you know, when you find a slope, you find it along certain paths, right? So if I take this graph, I could actually get a good idea. And when I say graph, the two-dimensional one that was plotted, I could actually get a good idea of the nature of the slopes associated with the three-dimensional surface, because the wider the level curves are apart, the shallower the slope, right? The closer they are bunched together, the steeper the relationship is, right? So it's kind of cool that you can kind of see them in, in real time, plotted adjacent to one another, right? So that's the idea. Let me just bring back my whatchamacallit. Right, so just looking at this again, because this is what I did was I did some screen captures. You're looking at the wider spacing here.
Audio.
Translates to shallower, quote unquote, slope in the 3D figure along that path. So for example, if I just wanted to follow this path here, this outward, and I'll actually do it from the origin. I just want to follow this path, for example. I'd be looking at something that has a relatively shallow slope, shallow followed by steeper, right? Transitioning steeper. So if I were to do that, I'd be thinking, okay, so I'm talking about a graph that starts off kind of shallow and then it gets steeper. Right? That gives me a little idea of what's going on there. Right? Then I could do the same thing in this direction. I could do the same thing in this direction. And so I would get all the different pieces that make up, and doing it in the backward direction is a little trickier. Best I got. I'd get all the pieces that make up a parabola. Which is why I never draw these things by hand, because you could see what I bring to the table here. Right. So, and specifically a circular parabola. Right. By the way, this is supposed to end up looking something like that. And as you can see, not so good, because I'm pretty bad at that. And even before technology, when I would teach this material, it would be a disaster. There was a lot of like, imagine this wasn't a terrible diagram. Now I actually have what I was going for. So, that's the idea. But you can get a sense of what's going on. Now, the one thing that people always come back to is like, well, how do you know it's not like this? That's shallow, and then it goes steep from there. Well, it's got to be differentiable over the interval. And if you have a corner in a graph, then it's not going to be differentiable. So we wouldn't consider anything like that. It would have to be a smooth curve. Right, so that kind of takes a lot of the guesswork out of it. This is really one of the few ways that this could actually shake out. This one is bothering me. Right, so that's the value of a level curve and contour a set of level curves in a contour plot. But again, like I said, it's sort of like an outdated concept, in the sense that we don't really need it to see the three-dimensional graphs. In the past, like when I was a student, back in my time, we needed these things in order to get a sense of what the surface looked like in order to do the calculus. So now it's not really so necessary. But if you look at example 5, it's find and graph the level curve of a function corresponding to c equals 15, then create a contour map for this function. You can see how creating a contour map would be disastrous, but it's really not that difficult. It just takes a little while. All right. So what we're doing is if we're given a function, in this case g of x, y, that looks like it's a conic section in some capacity, then first thing we would want to do is get it into the appropriate standard form for that conic. All right. So I would write this as x squared minus 6x. I'd leave a little space to complete the square.
So I am performing an analysis of variance using the AOB function. Given the formula structure, I have my y variable squiggle x dependent squiggle independent. So bodily size, my continuous numerical variable squiggle family, my categorical independent variable. And then I'm just wrapping that inside of the summary function. So
I think you need to mute yourself, Jasmine.
Stored the product of the thing.
Yeah, that's that whole multitasking thing.
But in this case, just to show you, you can wrap functions inside of other functions. So here I'm just running summary on.
Jasmine, you don't want to mute.
Okay.
So here's.
I guess I can take care of that. Oh, it looks like you got it under control. Yeah, sometimes I like to listen, because what I found out from a student who wasn't doing so well in one of my other classes, that that when he didn't understand something in my class, what he would do is instead of asking a question, he would look it up on Khan Academy. I was like, okay, I mean, or you could just ask the question. That's another possibility. You live, you learn. But that I couldn't tell. I heard something like categorical variables. That sounded like a statistical concept. So I don't know. I try not to take too much offense to things. So I'm going to complete the square. And when I complete the square, I take my b value, cut it in half, and square it. So it's going to give me a +9, but I correct for that. I'm going to take my b value, cut it in half, and square it. That's going to give me a +1. And so I correct for that to keep the equation balanced. All right, so that gives me something a little bit friendlier, x minus 3 squared. Now, if you're using technology, you really don't need to do this. It's just, it's worth it to kind of get a quick look at, like what it is that we're working with here in terms of the types of conic sections. So this is, it has a circular look to it, right? Now, in terms of the structure of the equation. Now, if I let c equal 15, where c is equal to z, so z equals c, and c is defined as 15 because this is our set of level curves, set of z values, it's really the levels that give level curves. What this question is asking me to do, at least initially, is focus on just the level curve when z is equal to 15. So at c equals 15, z equals 15. If we already know, because remember, a multivariable function of two variables can be defined, as like g of x comma y, but we could also call it z. That's another way of representing z. If it's in terms of x and y, I now have two equations defined as z, so therefore I can set them equal to each other. and come up with 15 is equal to x minus 3 squared plus y plus 1 squared minus 10, add 10 to both sides, and we got x minus 3 squared plus y plus 1 squared is equal to 25. All right. So what is that? You know, you look at it at first glance, you know, in its original form, x squared plus y squared minus 6x plus 2y and all that stuff. You might say, well, I don't know, but now it's pretty clearly a circle. A circle with center at 3, -1, and a radius equal to 25. All right, so for that, and the associated graph, I can go to Desmos. And honestly, I didn't go to Desmos to help me come up with the graph itself. I went to Desmos, you know, to actually do the physical drawing of the graph, and I didn't want to do it. All right. Thank you. It is indeed 5. So we have our circle, and that's associated with a particular level. Now, what we can do is take a look at Geogebra and see what this whole thing looks like. Let me do a quick I'll hit the waffle. 3D. Z equals x squared plus y squared minus 6x plus 2y. And let me just get rid of that plane again. We don't like the plane, we like the grid. Oh, not the projection, the grid. All right, so I'll hit home. You know, I kind of like to see at least the heart of the graph, you know, get some of the bits and pieces here. All right, now, if I graph along with that equation, the z equals 15, you see that it does intersect that curve in a circular fashion. All right. So then it just kind of begs the question of, okay, well, what would be the equation of that intersection? All right. So if we change our orientation, we're really just asking ourselves, could this have a center at 3, -1? Sure. Does it look like it has a radius of 5? Yeah, it could. So it seems to be fairly confirmed that the intersection of this plane and the surface itself is creating a circular path. All right. The contour map part, like I said, that would be too much. It takes a lot of work and not much of a payoff. And also, I just showed you how you could do it using technology, and I just showed you an image of what it's gonna. I want that to stay put. What it's gonna look like after we create it anyway. So it's kind of a waste of a question. So I'm gonna toss that, and I'll take it as a typo. Right. So that was just a little bit of a taste of the idea behind a level curve. Now, if you're given a contour plot, there's actually a fair amount you could do with something like that. So let's go to the next page, talk about things like you know, weather maps and topographical maps and things of that nature. You can see the blurb here, weather map in the figure below shows a contour map of the temperature function for the states of California and Nevada at 3 o'clock in the afternoon on a day in October. The level curves, or isothermals, join locations with the same temperature. partial derivative t of x, or t sub x, sorry, at a location such as Reno is the rate of change of temperature with respect to distance if we travel east from Reno. All right. T sub y is the rate of change of temperature if we travel north. But what if we want to know the rate of change of temperature when we travel southeast towards Las Vegas or in some other direction? Directional derivative enables us to find the rate of change of a function of two or more variables in any direction. All right, so directional derivative associated with a contour map. All right, so pretty interesting stuff. Now, if I superimpose a circle over this with Reno as the center of that circle. Now, I don't really have a compass to do this, so this is going to be a hideous looking diagram. But if I were to assume that Reno is the center, let me actually do that in black. And we're going off to Las Vegas. We'd have a circle with that radius as its length. All right. So I'll get rid of the irrelevant pieces in a second. But the whole idea is to show you how this ties together with partial derivatives in the way. All right. So, oh, that's an eraser. Zero degrees, 90 degrees, just giving it a little sense of scale here. Right now, it's saying that it's, Las Vegas is in a southeastern direction, just because we want to keep these problems as friendly as possible. We're going to assume that that means it's 315 degrees. All right, so we could call that negative 45 degrees. Right, if it's something other than that, if it's an angular movement that's, if I say southeast, I mean a 45-degree movement below zero, in the clockwise direction. But if I want it to be something other than 45 degrees, I'll actually give you the angular measure. Right. And if it comes to a question involving gradient or directional derivative on a test, I don't mince words. It'll be, I won't even say southeastern, southeasterly direction. I'll say in a southeasterly direction in parentheses. That means 45 degrees in a clockwise direction, something like that. I'll make it obvious to you. All right. So the directional derivative relation, we can go back. I mean, it's only a few pages prior, but there isn't really, actually, where? I don't even know where it is. So it doesn't even really matter. Oh, yeah, well, it's right. So the directional derivative relation for a function is, something you could refer to because everything is really essentially an open notes assessment. But more importantly, if you know the angular movement, you can use these examples as sort of a model, right? Because the unit vector in the direction that you're looking at is associated with cosine comma sine, right? So if you know the angular movement, then a lot of this work is kind of done for you, right? So I would actually kind of get in the habit of using sort of a, I don't want to say a hybrid because that word is so overused these days, but sort of a modified version of the directional derivative relation. Because if you really think about it, what we have here, if we combine the rules, and so this is back on page 60, if we know the angular movement, then the directional derivative is the dot product between the first order partials and cosine theta sine theta. Right. So if you have those first order partials, then all you have to do is multiply them by cosine theta sine theta respectively, and add them together, and you have your directional derivative. Then it's just a matter of evaluating at a particular point, right? So let me show you here what that would look like. Right? So we'd have du, d sub u, f of x comma y is going to be equal to f sub x cosine theta plus f sub x y theta, sine of, I don't know why I said y theta, sine theta. I even said f sub x, so I don't even know what that was right now. F sub y sine of theta. All right, that's a general rule that has been modified to suit our needs right now. All right, now we have a few things going on here that are going to kind of throw a little wrench into the whole thing. One is distance, coordinates and distance and things of that nature. Right. The other thing, which we'll get to in a second, is related to the first order partials and what they actually mean in this context. Right. So if I say at least the cosine theta sine theta part, that we're looking at really f sub x cosine of negative pi over 4. I used degrees already, so I'll just leave it like that. Of negative 45 degrees plus f sub y sine of negative 45 we're looking at f sub x multiplied by a radical 2 over 2 plus f sub y multiplied by negative radical 2 over 2. All right. So now it's really just a matter of getting our partials involved here. So that goes back to the little blurb here. Well, let me get the t sub x first. T sub x at a location such as Reno is the rate of change of the temperature with respect to distance if we travel east from Reno. And T sub y is the rate of change of temperature if we travel north. All right. So that's basically telling us east-west relation, north-south relation when it comes to rate of change for temperature. All right. Now, that part is kind of weird because it's saying it's kind of limiting it as just an easterly direction and northerly direction. The direction has actually been accounted for by the cosine function and the sine function. So these values will be rate of change from the beginning of your journey to the end of your journey in terms of the temperature per unit of time. All right. So what we would need is to decompose our triangle into horizontal and vertical components. All right. So basically, and I'm going to need to kind of clean this up a little bit. Where am I going? Let's see if I can make more of a mess out of this. I think if I just move the y-axis a smidge, I think I can kind of get where I need to go. So if I go in the easterly direction, let me do the southerly direction first. You want to be thinking about what barriers we're going to be crossing over. All right. So in the southern direction, we have to get down to the level associated with Las Vegas. So I'm going to make this a set of dashed line, or a single dash line. All right. So we have a vertical movement followed by a horizontal movement. Now it's we have a little bit of gray area here, but what we want is the transition between temperature zones beginning to end, and then the transition of distance based off of the scale that they gave us. Now let's see. Okay, it actually didn't wipe out the whole circle, which is good. All right. I actually don't need all of this circle, so I'm just going to wipe this out. All of this part of it. I'm just cleaning up a little bit. All right, so what I'm going to do, like I said, let me just get my pen to be a little thicker here. We're going to account for the vertical movement and the horizontal movement. Well, that's already finding green, so we're good there. All right. So again, it's a rate of change of temperature based off of the distance travel. Distance travel, we're going to get an estimate of an answer, but it'll at least be something. All right. So in the mess of a graph that I have here, or diagram, I'm looking at the green area associated with Reno. Right. So that's in the green zone. Right. So Reno the X value, we're talking about the rate of change of temperature as the Y value, but the X value is the horizontal distance traveled. All right. So Reno, in terms of, why is that moving like that? The X component and the Y component. Reno is our start point, so it doesn't have any horizontal movement or vertical movement. All right. So then in terms of the temperature, the Y value is the temperature that we're going with. That is in the 60-degree isothermal range in both cases. All right. So it kind of begs the question, well, why did I break it up into horizontal and vertical components? Because what I have to do is use this benchmark, and from there, I have to find the slope between this point and the point directly below it. Right. So now I need south of Reno. All right. And I also need east of Reno. I'll do east first. Unlike somebody speeding through a parking lot. All right. So I can go south, then east, or I could go east and then south. It really doesn't matter which way I go. Now, since I know that these are going to be parallel relationships, let me just get that green. I can plot it on the 0 line and create a rectangle out of that, because it's really just the question of which way is more convenient. You know, like in this case, we're just going from endpoint to endpoint, so it doesn't matter. But if you needed to stop along the way, let's say I needed to stop at this point over here, then, you know, I'd have to cross over a bunch of little isotherms in order to get there. But it really doesn't matter. But the reason I just drew that out for you is because I just wanted to make it clear that whether you go this way and then this way, or if you go this way and then this way, it's not going to matter. All right. All roads lead to Vegas. All right. So if I go east of Reno or south of Reno, either way, I'm going to end up with another point. All right. So let's say I decide I want to go along the green path here to go east of Reno. All right. So that gets me to a fixed point at this location. All right. In terms of distance, that's the tricky part. Right, because we have to ballpark it, and that's one of the reasons why this is very, very much an awkward problem to have on a test, because I'd have to eyeball it and say, all right, it's 1. I tick mark it off here. It's like 1.5 of these scale values. All right, so 200 plus another half of that distance would be 300. So the distance traveled would be 300 units. Now the temperature, it appears to be in the 70-degree zone. That was the easy part, because south is where it gets tricky, because what I have to do is somehow rotate this. It's really only tricky because I'm doing it on the device here, but it looks like it might be a smidge more than 200. It's so hard to tell, right? Because once I resize it, rotate it, it tends to want to resize. So that's 200. If I resize it, I'm gonna try to be careful and keep its size. It's on a little bit of an angle. Yeah, it's a smidge more than 200. Like, what is a smidge? You know, like, what do we quantify a smidge as? I would say it's probably like at this location here, maybe like, 10 units. So I'm just gonna eyeball that, and I'm gonna say that the vertical distance, or the distance traveled, is 10 units. Well, I'm sorry, 210 units. And that one is still in that little beige zone, just barely though. Still in that beige zone. So we're looking at still in the 70-degree zone. All right. So this point would correspond with this one in terms of finding the slope. So that's really related to an easterly movement. So f sub x is going to be that rate of change, 70 minus 60, which is 10 over 300. F sub y, and so let me highlight that appropriately. That's this one. F sub y is going to be 70 minus 60. So 70 minus 60 is 10, still 10. Over 210 minus 0. So that's related to these values. So we did it a piece at a time, basically. Right? And so our directional derivative and it ends up being an approximation, 10 over 300, that we can simplify that to 1 over 30. We're looking at 1 over 30 times radical 2 over 2, plus, and this one would be 1 over 21 times negative radical 2 over 2. So then radical 2 over 60 minus radical 2 over 42. And, for the sake of just having something that seems kind of clean, I'll simplify a little further. I'll just do 1/60th minus 1/42. I'll frac that up, slap a radical 2 on it, and we're looking at negative radical 2 over 140. All right. So negative radical 2 over 140 would be our directional derivative. Now, the thing that we got to keep in mind here is that this directional derivative approach, because we didn't come up with a function, it has an expiration date, right? Because the units here, very important, the units are related to temperature and distance in miles. So this is really saying degrees per mile. All right. What the directional derivative does, what it gives you is a rate of change. What it doesn't give you is a permanent rate of change. And in fact, if you really think about it, this number in the long run isn't going to make a whole lot of sense, because we're starting off in a 60-degree zone, and it's telling us that our temperature is going to decrease as we move closer and closer to Vegas. Now, if you've never been to Vegas, maybe you don't know, but it's pretty freaking hot there. All right. So if anything, it should be going in the opposite direction. But what this is telling us is that as we start moving in the direction of Vegas, our temperature is decreasing at a rate of radical 2 over 140 degrees per every mile traveled. All right. But then there is something that happens along the way where the temperature starts increasing again. Right. So what a gradient gives you, what a directional derivative gives you, is it gives you a rate of change. It's like linear approximation from Calc 1. It gives you a rate of change very close to the point of interest. But the further you move away from that point of interest, the less meaningful, I guess, that number is. And so what ends up happening is like little minor course corrections. You know, if you've ever, I mean, my dad used to be big into submarine movies and, you know, basically anything like machines of war. So you'd watch any kind of submarine movie. There's always a scene where they're on the bridge or they're at the con and they're kind of piloting the ship, if you will. And they're saying, okay, we need a 3-degree down bubble, you know, set course for blah, 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 mark, blah, 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 mark, you know, like whatever. And so it's kind of cool to hear like the cadences and the orders being barked from one person and instantaneously following the orders without question, you know, for the good of everybody. There's that part of it, but then there's also the part where it's like, how do you figure that out so quick? And if you ever watch Hunt for Red October or Crimson Tide, or, you know, like the good ones, and there's even older movies, they usually have a big map, and on that map you'll see the ocean depth, you'll see a surface map of the ocean floor, you know, and all that stuff. But you'll also see like little minor course corrections, and it'll always be like, all right, go this direction for this long, then correct to go that direction for that long, then that direction for that long, then that direction for that long. You know, it's never just point and just keep going. Right? Just think about all the little minor course corrections that you make when you're driving your car, even when you're on a straight roadway. Like you're just 684 is probably as straight as it gets. But you'll find yourself, I mean, it's not like you can just hold the wheel or lock it into place and close your eyes and be good for the stretch of the highway. Even the part where it's actually a straightaway, there's always little minor course corrections that need to happen. It's just we do it so intuitively that we don't realize we're doing it. All right. So this is actually the first little minor step. And it's possible that there needs to be a recalculation of the directional derivative after the first mile and ongoing. So the pathway, it might be like that old school problem, you know, that gets you interested in polygons, where you say if you start off with a triangle and then include another side, then you get a rectangle. And then you include another side, you get a pentagon, and then you get a hexagon, a septagon, octagon, blah, blah, blah. And the more sides you include, the more circular it gets. You know, like if you had lots and lots of sides, let's say you had 100 sides, it'd be a 100-sided polygon. It would look very circular, but it have like tiny little segments that make up that circle. That's the same idea. It's move a little, correct. Move a little, correct. Move a little, correct. Move a little, correct. That's what a directional derivative does. All right. So this kind of problem, very, very challenging to have something involving a weather map on an assessment, but there is ways to get the directional derivative. If you look at the practice test, you see what I'm talking about. All right. So I didn't want to beat this one to death. What I'll do is I'll suggest that maybe you tackle the next one, and I'll post the video solution for it. But I'll put video solutions for numbers 8 and 9 also. But I don't think if you get number 7, then you're good on this concept, and you don't really need to spend too much more time on it. All right. So yeah, that's where I would leave that. So what we're going to do is shift gears and talk about integration now. Very exciting. Okay. Integration, partial integration, and then multiple integrations, multiple integrals, which sets us up as we go forward to talk about some pretty advanced topics, and kind of gets us into the transition into the third unit, which is vector calculus. All right, so a lot of fun stuff coming your way, but a lot of stuff that needs, a solid foundation in the material that we've been covering. So I'm thankful to have your undivided attention, of course. Attention being the word of the day. So, and I've decided, because I've been a kind of a slacker when it comes to the word of the day, I'm going to make it a point from here on out to have multiple words of the day. So just be on the lookout. So I just gave you the first one. All right. So there's more coming. All right. So partial integration, along the same lines as partial derivatives, we're integrating one variable at a time. All right. So what does that mean? Well, it means that we're holding a variable constant while we're integrating with respect to the other. So now there's tons of applications of this, and there's more to it in terms of the conceptual understanding, but in terms of practically speaking, there's really not much more to it than that. All right, so if I'm going to integrate this with respect to y, what I'm going to do is I'm going to treat x as either a constant or a constant multiple. All right, so treat x as either a constant or a constant multiple. If it's, and all I mean is either a standalone constant or a coefficient in some capacity. Because in this case, we don't have an expression or a term that involves both an x and a y, but we could, as you can see in the example right below. Right. So antiderivative with respect to y of 2x. Well, after 2xy. All right, because the y wasn't there. Now, if we integrate, you kind of, like when y is not there, we kind of have to assume that it really is there, just with a nice little y to the 0 term or factor associated with it. All right, so this is implied. All right, so if I integrate with respect to y, I increase the exponent of y by 1, so y to the first power, and divide by my new exponent. So 2x divided by 1 becomes 2x. So that's fine. The y squared gets integrated the way it always is. So increase the exponent by 1, divide by the new exponent. So 1/3 y to the third. The issue is that the new ingredient here comes in the form of a constant. In the past, we would say plus c. All right, so I'm going to write plus c here, but we do have to make an adjustment to that. All right, because c represents any kind of constant, but we could also have what we call a constant function. And specifically a constant function of x. Because, yeah, if I take the derivative of a constant, it goes to 0, which is why we always put a plus c for indefinite integrals, Calc 1, Calc 2. But now any expression that's there that's solely in terms of x would actually differentiate to 0 as well. All right, so in my check, and you don't have to do a check, but just for this one problem, I'll do it. If I wanted to check this by differentiating with respect to y, the 2xy plus 1/3 y cubed plus c of x, we check by using the techniques that we learned in the partial differentiation part of the unit. Right? So the derivative of 2xy, the derivative of y goes to 1. So we're just left with the 2x. So that checks out. Or you could even look at it and say, well, I got a y to the first power, multiply your power by your coefficient, reduce the power by 1, same deal. All right. I just realized that this doesn't look like a 0. It looks like a disaster. So let me just clean this up. All right. The derivative of 1/3 y cubed, that's easy enough. 3 times the 1/3 is 1, y to the second, so that's fine. But then this one, in my check, what I could do is I can just say, okay, well, let me suppose that this is like the sine of x. If it's a sine of x, so I'm just making an example off the top of my head. If it's a sine of x, what would its derivative be with respect to y? Well, it doesn't have a y in it, so it would be 0. All right, so maybe it's not a sine of x, maybe it's e to the x. E to the x normally would have a derivative of e to the x, but derivative with respect to y, there's no y in there, so that would go to 0 also. All right, so maybe we say 2x squared plus sine x plus e to the x. Not a single y to be found. This whole thing goes to 0. Right, so any function of x would get the job done. But this is it's a catch-all. It would actually include constant values as well. Right, so because I mean you've had plenty of instances where you'd have, you know, over the years where it's f of x equals 2, for example. I mean, I could graph that. It's a function of x where the independent variable is x, but the independent variable is not written in the function, which means that it's true for all values of x. All right, so that's fine. You could have a constant as well. So this covers anything except for an expression that is the product of x and y, or includes the product of x and y. All right, so we need to make sure that we have that included in our process. It's like kind of like we're updating our terms and conditions. All right, so now, okay, so now I just got to make sure that that's included in there as well. All right. Looking at number 2, I'm anti-differentiating with respect to x now. So now the relevant variable again is x. Antiderivative of 2x would be x squared. Antiderivative of y squared, well, there's no x to be found, which means that there's an implied x to the 0th, which would anti-differentiate to an x to the first power. So this becomes y squared x. Right? But now what I need to do is tack on a constant, an integration constant that is a function of y. No x contained in it. That would differentiate down to 0 through the checking process. All right. So that's a little bit of a twist. It takes a little getting used to, but we need to get used to it because, as you can see, in the problems that follow, we're going to be performing what we call multiple integrations. All right. So one integration compounded upon another. All right. So, and you'll see. But these problems are actually kind of nice because they're definite integrals. And we're going to be doing a lot with definite integrals as they apply to multiple integration. All right. The calculator becomes a really good resource, as you know, to kind of cut out a lot of the unnecessary, I'll call it busy work. Right. But it's really just the Calc 2 stuff that, honestly, when I first started teaching this course a while ago, I got caught up in the Calc 2 stuff, where I found myself never taking off credit for the Calc 3. Everybody was getting credit for the Calc 3 stuff. The only thing that people were losing credit for was the Calc 2 stuff. So I tried my best to reorchestrate or reorganize the course so that the Calc 2 stuff isn't as emphasized. Right? You know, there's some things that need to be there, but I tried to kind of filter out as much as possible so that you're on the hook for the Calc 3, and you still need to know some Calc 2, but not. I didn't want it to feel like you're taking Calc 2 again. Right? So all that is my way of saying, use the damn calculator, please. Right? When we're taking the antiderivative in the form of multiple integrals, we work inside out. Right? So the innermost integral is the one we account for first. Right? What a lot of people do, and I don't like doing what I'm about to suggest to do, but a lot of people do is they'll just rewrite it, stripping away the outer stuff, kind of pretend that that stuff's not there, just rewrite this as its own problem. I don't like doing it that way, only because you see what I just did. I just drew a nice red rectangle around the relevant part. It's pretty clear what I intend to work with. All right. So, but I'll leave the organization part of it up to you. In the past, if it was a function of one variable, if your integrand only contained one variable, then you just dump it right in the calculator, be done with it. Here it's got two variables, so there is no popping it into the calculator. We need the intermediate step where we work through the first integral before kicking over to the calculator to evaluate the second integral. All right. So I'm integrating with respect to y. So I'm looking at term by term each of these. The antiderivative of y is 1/2 y squared. So this is 1/2 xy squared, because the x is treated as a constant multiplier, is just coming along for the ride. All right. So that's that. Then what we have to do is integrate the second piece. Again, with respect to y, the antiderivative of y to the third is 1/4 y to the fourth. So 1/4 x squared y to the fourth. This is being integrated over the interval of 0 to 2. All right. So, sorry. So now what I want to do is apply the fundamental theorem of calculus by substituting the relevant variable here is y. So I'm going to substitute the 2 and then the 0 in for the y's. And so what I should end up with is an expression in terms of x. So 1/2 x times 2 squared plus 1/4 x squared times 2 to the fourth minus, if I plug in a 0 for the y's, that's just going to zero out, so I'm not worried about it. All right, 1/2 multiplied by 2 squared, 1/2 times 4 is 2, so 2x. 2 to the fourth is 16, multiplied by 1/4 is 4, so 4x squared. All right, so that's my first antiderivative, specifically definite integral over the interval of 0 to 2. All right, now I'm going to integrate the remaining expression over the interval of 1 to 3 with respect to x. All right, now this part, because we're now down to a single variable expression, feel free to put it right into decimals. All right, so you go to functions, miscellaneous, selected the one that looks like an integral, over the interval of 1 to 3, parentheses for your integrand, 2x plus 4x squared, close it up to encapsulate the integrand, and then slap on a dx. If it gives you something that's fractionable, just for the sake of having a, something easy to type in on Blackboard if you're taking a test, I would recommend fracking it up and going from there so you don't have to worry about rounding. All right. I keep trying anyway, the best I can, or the best I could, to give rounding instructions for problems that I know are going to end up being the kind that you have to round on a test, on the test. So I'd like it to be the general rule of thumb, so that, let's say you're tackling a problem where you get an answer like this, that the directions kind of give you a little guidance as to what what you would expect to get as the type of answer. Like if I don't give you rounding instructions, I typically mean that to mean that you should be getting a clean answer. If I do give you rounding instructions, then expect something that's pretty hideous, right? So that's the idea. Sometimes I slip up, but when you're taking the test, if you're in doubt on that, just ask. Right. Now you see here, we're looking at a triple integral, very spicy. Right. So we work inside out. I mean, we could have like a quadruple integral. We could have a quintuple integral. It doesn't matter how many D's there are. It just means the same thing. Work inside out, integrate, get an answer, integrate again, get an answer, integrate again, keep going. Keep going till you can't go no more, right? So this one is with respect to x. So you're looking at z times the sine of y. At first glance, it looks like a pretty spicy problem, something that maybe we're going to be working on this for a long time. I don't know. It looks pretty tough. But then when you realize, wait a minute, there is no x. There's no x in that expression. That actually simplifies the problem a great deal, because the absence of the x is telling us that this whole expression, no matter how hideous it is, that whole expression might as well just be a 2. I mean, it's a constant. We're treating it as a constant. So it's going to be z times the sine of y multiplied by x. So what I'll do is, just to kind of keep it a little bit more organized, I'll just, no, you know what? Alphabetical order. How about that? For the most part. xz, right? That's being integrated over the interval of 0 to the square root of 4 minus z squared. So that's a little bit crazier in terms of the bounds. Why is it dx and the partial integral is not delta? Oh, that's a good question. It actually really is a set of deltas, and that's a really good question. It's actually a set of deltas, except somebody decided along the way that it's too much of a pain to write deltas every single time. So it's kind of like a form of laziness to write it as d. But those actually are lowercase delta. In fact, every time you find an antiderivative, those are supposed to be lowercase deltas. Even back to Calc 2, Calc 1, Calc 2, it's just it just morphed into a d over time. All right, but they really are deltas. Now, there are exceptions to that, because if we could define the function, like you take the antiderivative, you go through the entire process, and it turns out that your final answer is not a multivariable function, like you get z equals something in terms of just x or something just in terms of y, then you would actually have license to say, no, it really is a d. But in every other instance, it is a delta. All right, so good question. I like those kind of questions. And I've always been fascinated by the notation, and I've always been very disheartened when the answer is basically the answer I just gave. No, it's just somebody decided that that's how we're going to do it. I'm like, really? That's anticlimactic. No, but unfortunately, in this case, that's what it is. All right. So this is over the interval of 0 to 4 minus z squared. I was going to make anticlimactic another word of the day, except I'm not even sure I'm saying it right. Anticlimactic. All right. Yeah, so that'll be the second word of the day. And just for the hell of it, I looked it up just for the spelling. But there's a nice definition staring me in the face: causing disappointment at the end of an exciting or impressive series of events. Anticlimactic, your second word of the day. Or WOTD, for those of you who like acronyms. All right. So the 4 minus z squared radical and the 0 are what's getting swapped in for the x. So what we're looking at here, when we simplify, is z times the root of 4 minus z squared. And then we have our sine of y. All right. Now, this is a multivariable expression that contains both a z and a y. So we can't go to the calculator yet. But what we can do is work. Let me just get a fresh new color here. This next level of the process is going to now incorporate the 0 and the 2. And now we're integrating with respect to z. All right. Now, I will tell you that there is a nifty little shortcut to some of this, but the shortcut doesn't always work, and I haven't properly introduced it. So, yeah, that's kind of it's not the appropriate place to include it. What I can do is come back to this example with the shortcut later on, but for now, we're just going to go through it the long, boring way. And by boring, I mean incredibly exciting. So what we need to do is anti-differentiate just the z portion of this. All right. So it looks like we got a little u substitution going on there. All right. So I'm going to let u equal to 4 minus z squared, which makes du equal to negative 2z dz. All right. So if I'm just looking at this stuff here, I'll box it. This, along with the dz, I see I now have the means to get rid of the 4 minus z squared. All right. But I got to get rid of the z and the dz also and replace that with a set of u's. So let's do that. I have a negative 2z dz. If I multiply both sides by negative 1/2, that gives me the relation that I'm looking for. It gives me the droids I'm looking for. Z dz is equivalent to negative 1/2 du. So now I can write my integral, my definite integral, as negative 1/2. Instead of the square root of 4 minus z squared, I can now write the square root of u, but instead of the square root, I'm going to write it as the power of 1/2 du. Right now, the bounds are a different story. I mean, it's up to you. What a lot of people like to do is leave it boundless until the anti-differentiation happens and then bring the old bounds back. But these are actually some pretty clean bounds. All right, so we have a function that relates u and z. U is equal to 4 minus z squared. These are z bounds. All right, they're bounds associated with the variable z. All right, so it might as well say from z equals 0 to z equals 2. All right, so what I want them to be is u bounds. So what I would do is evaluate my u function for 2 and for 0. And when I do, I pop in a 2 for z, I get 4 minus 4 is 0. Pop in a 0 for z, I get 4 minus 0 is 4. All right, so from 4 to 0 would be my brand new bounds. And now I don't have to worry about reversing the substitution process. All right, so increase the exponent by 1. Oh, lost my sign. Sign's still got to be there. You can't just ditch it. So sine of y. So increase the exponent by 1. 1/2 becomes 3/2. So u to the 3/2. Divide by the new exponent. So it's the same as multiplying by 2/3. We're looking at negative 1/3 u to the 3/2. Can't just forget the sine of y as much as I keep trying to. Over the interval of 4 to 0. All right, so it's a little bit of a backwards relationship, but that's okay. You can handle that one of two ways. You could swap the bounds and then therefore negate the integral. Or you just work with it as is. That doesn't really make a difference. All right. So it's really up to you. I'm going to leave it as is because the numbers are kind of friendly. So it's not like I'm saving myself too much time and energy by making a replacement there. All right. But just an old rule from definite integrals back in Calc 1, Calc 2. If you ever want to swap the bounds of an integral, you can do so as long as you negate the integral itself. All right. So, but like I said, I'm going to leave it as is. If I plug in a 0 for u, I get a result of 0. So 0 minus, that's a little too thick now. Negative 1/3, 4 to the 3/2 times the sine of y. All right, two negatives make the positive. Boop, boop. Square root of 4 is 2, cubed is 8, so 8/3 sine of y. All right, the bounds have been accounted for, so we're good there. But now it's just a matter of integrating this last expression over the interval. Let's see, I haven't used red yet. With respect to y. Well, that was hideous. I had no excuse for that one. I took my eye off the ball there. All right. So we're integrating this one over the interval of 0 to pi with respect to y. Now, this is not difficult to do by hand. So it's up to you. You can do it by hand or you can do it in the calculator. I don't begrudge you either way. All right. So, you know, in all honesty, it's probably just as easy to do it by hand as it is to type it in. So antiderivative of sine is negative cosine. So negative 8/3 cosine y over the interval of 0 to pi. So we're looking at, if I plug in a pi, negative 8/3 times negative 1 minus negative 8/3 cosine of 0 is positive 1. So we're looking at the two negatives making a positive, two negatives making a positive. So 8/3 plus 8/3 is 16/3. You know, for giggles while I'm here, why not, right? Because we're going to use sine instead of, I'm sorry, we're going to use x instead of y. So that makes never mind. So you get 5.3 repeated, converted over, 16/3, either way. You know, 6 of one, half a dozen of the other, as they say, whoever they are. Just a little housekeeping. All right. So, you know, that one's a little bit more involved, obviously. A lot going on there. But really kind of having nothing to do with the Calc 3 of it, having more to do with the Calc 2 of it. The thing, I mean, if you compare the level of difficulty between numbers 3 and 4, aside from the fact that one had an extra layer of integration, you're really just looking at the fact that you had a more complicated substitution after the first integral, and also a little u sub, you know, a little bit more complicated in terms of the integration, right? But aside from that, I mean, same level of difficulty, but you know, it's really a matter of the Calc 2 being the determining factor of the difficulty level rather than the Calc 3. All right. So that's a little bit of a quick shot of partial integration. What I want to do now is give you a little taste of what it's used for. All right. So I'm going to put a star on number 5 with the expectation that because I didn't really introduce this idea in any way, it might be a chore. But if you give it a shot, you know, you might meet with some success. We will go over this one. It's a proof, but it's designed to kind of get at a particular concept, right? So it's something called Coubini Theorem. But what I wanted to talk about is the idea of double integrals and rectangular coordinates, specifically how you go about finding volumes using this idea, right? So, and this whole page is just kind of the typed out version of what I'm about to explain. So I'm just kind of hopping over it, right? So if you look at the example, you have, it says compute the exact volume of the solid of the surface, z equals blah, blah, blah. But it gives you a set of rectangular bounds. Right? Now, I wanted to actually take a minute and show you how you type in a restricted domain using Geogebra, but it'll take me actually going over to a laptop or a computer screen. So just bear with me for a sec while I set it all up. It's worthwhile. And the reason, I mean, not that I need to explain every single thing, but or at least my motivation for everything. It's just, I think you'll find this to be pretty valuable because sometimes these three-dimensional graphs get so crazy that that there is value in being able to truncate them. All right, so let me pause the recording. All right, so I'm going to type in the equation. Z equals, you know, the one from the example, x squared. All right, in case you want to know what x squared looks like. I mean, we played with that a little bit, so that shouldn't be too much of a shock. Sine of, let me get a division bar here, x, well, it's actually pi, so I'll just type in pi times x, I'm sorry, pi times y over 6. All right, and it gives you that graph. Now, when I hit enter, it actually changes the pi into a pi. So that's so you can avoid having to go hunting around for the pi key. I mean, it's pretty prevalent when you go to the keyboard, but it's one less thing to worry about. You know, if it's a notable Greek letter, generally if you just type it in, it'll show up. All right. But what I want to do is actually truncate this, because what you see here and what we have on paper are two vastly different things. All right. So what we can do is use the conditional if. Okay. So if, open parens, put in your conditions, which in this case are x bounds and y bounds. All right, so for this, I'm going to actually use the keyboard. So if I would say they gave us 0 is less than or equal to x, which is less than or equal to 6. I also want to include the bounds associated with y. So I want it to be the bounds of 0 to 6 for x and the bounds for 0 to 6 for y. So what I would do is actually put an ampersand in twice. So shift 7, but twice, and that'll convert it into an and symbol. And the reason I do that, again, is the same reason I type in pi. It's just so I don't have to go hunting around for the and symbol. If you know it's in this special characters menu, then go for it. It's just, I found it to be pretty convenient because it's and. So the and key is shift 7, the ampersand. You're just doing it twice, and it's a shortcut key to get you there. So it's kind of nice. Then I want to do 0 is less than or equal to y, less than or equal to 6. And then what I do is I just put in what the result of this expression should be based off of these two conditions. And the result should be whatever z is equal to. So x squared sine, so basically the right-hand side of the equation of pi times 6, pi times y, sorry, over 6. Now, looking at this, you can see that a new graph has appeared, overlapped upon the original graph. Right now, hopefully it's pretty obvious, especially if I zoom out. Sometimes it kind of loses the flavor a bit, but if I zoom out a little bit, you can see that in terms of x, it's only going from 0 to 6. In terms of y, it's only going from 0 to 6. In terms of z, it's going wherever z goes based off of that relation. All right, but we defined a new expression, a new function with those particular restrictions. Right. So what this allows us to do based off of given restrictions is really just get rid of all the stuff in the graph that we're not interested in. There's a whole lot of graph here. It's a periodic function because of the sign. There's a whole lot of graph here that we're not interested in. So to be able to get rid of all that is really valuable. All right. So I'm going to hang on to this and get into the actual problem, which says, and I'll go back to the iPad in a second, but it says, I'll just read the whole thing. Compute the exact volume of the solid bounded by the surface, the rectangle, which is got the boundaries of 0 to 6 for x and y, in the xy plane and the plane x equals 6. All right. First, using thin slices parallel to the xy plane, yz plane, then using thin slices parallel to the xz plane. And then we sketch some thin slices on the diagram below. All right. So what I'll do is turn on the labels to make it obvious what planes we're looking at. I think it's obvious which one the z plane is, but I'm sorry, the z axis is. I kept saying planes, I meant to say axis. So we can look at it this way. Where are you? There we go. So x towards us, y, the x and y towards z upward. Now, if I want to have a plane that's parallel to the yz plane, so here's y and here's z, I would want to have a plane that's defined as x equals some number. All right. So what I can do is create a relation in GeoGebra that kind of gives me an idea of the visual relationship. Now, to make this consistent with the graph on paper, I'm just going to turn it around just so you can see the outer part of the surface. But that's really what the graph looks like. I mean, and you could zoom out further and see that it actually gets closer and closer, but that's kind of beyond what we need, right? So what I can do here is create a function or an equation that's in the form of x equals some constant. All right, so I'll say x equals, I don't know, I'll say x equals c. Right, which would create a slider, and then you can see here that what's happening is a parabolic curve is being generated, or at least it seems parabolic. Right? It's getting cut off at the natural boundaries created by the restricted domain, but it does appear to be consistent with the shape created by this flow line here, this flow curve. All right, so as I move along, you can see it's taking on that shape, just getting stretched and shrunk as we move further and further along. All right, so I could turn that one off, but I could also, it's parallel to a YZ plane. So here's Y, here's Z. Oh wait, we already did YZ plane, XZ plane. Here's X, here's Z. That would be a plane along Y. So let's say Y equals C. Moving my slider, you can see it's going back and forth this way. All right, so it kind of has a look of something that sort of feels exponential in some capacity, even though we know it's probably not based on the nature of the function. It's probably more parabolic and we're only seeing a piece of it, but it does have that look where it's starting off at some shallow slope and then increasing in slope as we go. but it does seem to have some sort of parallel relationship. I'm sorry, parabolic relationship. All right. So let me pause the recording. Resume recording. At least I didn't get too far. All right. So it's going to have some height off of the XY plane. That's going to be associated with Z. But if I want the area in order to come up with the volume, then somehow I need to get this whole face. All right. So what I can do is kind of go back to my knowledge of Calc 2 when we talked about finding areas under a curve. What we did was we used the Riemann sum and we worked our way from one end to the other by coming up with a singular rectangle, defining that rectangle, right? Defining that rectangle's area, and then integrating that rectangle throughout the entire interval, or whatever the interval was in question. So we have all of this stuff. So all of these little rectangles and so on, propagating their way through or filling the space from one end of the interval to the other. I kind of went down this this rabbit hole, and now I'm stuck drawing the whole dang thing. This would have been a good time for me to go the imagine route. Imagine I use rectangles to fill the whole space. And you would have been like, oh, okay, yeah, sure, sounds good. All right, so I'm just going to choose one of these rectangles. I'll just take this one over here, and I'm going to define that. All right. So the area of that rectangle, let me just blacken that in, make it stand out a little bit more, or at least I'll do it like that. Right. So that is going to have a little tiny thickness or width right here. This width here is a movement along the y-axis. So that's a dy. Right? It's an infinitesimal width along the y-axis. So that's a dy. Right? The height of the whole thing, that's just z. It's dependent on where it is along the curve. So the height is equal to z. So I would say the area of the arbitrary rectangle is going to be z times dy. All right. Now, if I integrate that throughout the course of the face of this individual slice, this cross section created by the plane slicing its way through the surface, if I integrate this over that interval of 0 to 6, so it starts at 0, I'll do it in green. The interval starts at 0 and ends at 6. Then I would have at least the area of that one surface. That one slice. All right. Still doesn't give me volume, but we're getting there, because now what I can do is say, all right, well, if I take that and I tack on a little bit of thickness to it, which is why I drew it as a slice, and I gave it that little bit of thickness over here. I need to keep some of that. I lost track of my undos and my redos, so I'm trying to, oh, there it is, redo, redo, redo. Okay. This little bit here is a movement along the x-axis. Right? An infinitesimal little movement along the x-axis. So that makes that a dx. Right? So this together, these three pieces give me the volume of a single slice. right? Now, if I want the volume of all of them, then what I'd have to do is integrate from the beginning of this interval to the end in terms of x. All right, so we're creating a double integral over those respective intervals. And it's kind of like a general formula now that you think about it, because the only thing that's going to vary if you have a rectangular base area is going to be whatever z is. Now they told us that z is equal to, I highlight it, z is equal to this mamma jamma up here. So we're looking at from 0 to 6, another 0 to 6, x squared sine of pi y over 6 dy dx. All right. So then I'd just be looking to integrate that, and I'd have my volume over the interval. All right. So antiderivative of the sine function, because that's the only one that it contains a y. I use my color coding strategy. Antiderivative of the sine function is going to be negative cosine. So negative cosine, I have my pi y over 6. Now, that pi y over 6 is really the same as saying pi over 6 times y. When I differentiate, when I take the derivative of the trig function, I take the derivative of the function itself, and then I multiply by the derivative on the inside. When I go the other way, if it's a simple linear trig function, so a function, a trig function of a linear function, then I would just divide by the derivative on the inside. Right? Derivative on the inside is pi over 6 with respect to y. So if I divide by that, it's 6 over pi. So I'm looking at, oh, why is that? I don't even, if I wanted to replicate what I just did, I don't even know how to do it. So 6 x squared over pi. And you could just verify it because the derivative of cosine would be negative sine. That would wipe out the negative sign, S-I-G-N sign. The derivative of pi over 6y would become pi over 6, which would wipe out the 6 over pi, and you'd be left with the x squared. So we're in good shape there. And then what we would have to do is evaluate this over the interval of 0 to 6, substituting the 0 and the 6 in for y specifically. All right, so negative 6 x squared over pi cosine. If I plug in a 6 for y, I get a pi minus negative 6x squared over pi cosine. Plug in a 0, I get a 0. Negatives cancel. Cosine of 0 is equal to 1. Cosine of pi is equal to negative 1. Negative 1 is going to cancel with the negative here. So it's really 6x squared over pi plus another 6x squared over pi, which is going to be 12x squared over pi, which I'm going to write that as 12 over pi x squared. All right, because then next part of the process would be to anti-differentiate this with respect to 6, and then it's up to you, you know, do you want to do that calculator style or do you want to do it by hand style? You know, it's a simple power rule case, so maybe you just do this one by hand. So integrating with respect to x, increase the exponent by 1. I get x cubed. Divide by the new exponent, I get 4 over pi. Over the interval of 0 to 6. If I plug in a 0, that's going to be irrelevant. So I'm not even going to worry about that. But 6 cubed is 216. So what is that, 864 over pi? I have no idea. Let me just check that. Oh, look at that. What do you know? I mean, I've done this problem enough that I should actually just remember the answer, but honestly, I don't. I just did the 2 multiplied by 4, and then I did the 16 multiplied by 4. Now, the 6 cubed, I remember that because that comes up in my stat class like 1,000 times a semester. So it's not genius, it's just memorization. But anyway, this is a measure of volume. So this is cubic units. And so coming up with the solution to the other approach parallel to the XZ plane, I'll draw the diagram for you, but that's pretty much where I'm going to leave it because I want you to have the opportunity to try this on your own. So we'd be looking at something along these lines when it got sliced through. Now, because it doesn't have a top to it, it doesn't have a cap, kind of hard to see what's going on over here. It's going up forever, really. But you got to imagine, because it is a continuous function, that it's going to eventually meet up somewhere, up top. I just don't know where. Actually, this line took off on me, so I'm going to fix that. So you got to figure it's going to come up somewhere. We don't know where. And then it'll make the journey back down. But you're looking at a slice, something like that, something in this neighborhood. So you'd have a thickness along the y-axis, so that would be your dy. And then what you would do is create an arbitrary rectangle over here. Try that again, shall we? Create an arbitrary rectangle over here. It's going to have a thickness dx. Honestly, I've already started doing the problem, so I might as well just keep doing it. So z would represent the height here. So it would be z multiplied by dx integrated over the interval of 0 to 6. Integrate being the last word of the day. And then applying the same idea of like, okay, once we figure out the area of that face, we incorporate the thickness, the dy, and integrate that from its beginning to its end. But we'd be looking at a function that looks similar but different, right? So it would be the antiderivative over the integral of 0 to 6. The function is x squared sine of pi y over 6, but I say pi over 6y, dx followed by dy. This one actually ends up being a little simpler, because when I take the antiderivative of x squared, I get 1/3 x cubed. The sine comes along for the ride over the interval of 0 to 6. Still a pretty simple computation. If I plug in the 6, I get 216 over 3 sine of pi over 6 multiplied by y. If I plug in a 0, it zeroes out. So that's this middle part taken care of, or the first part of the iterated integral. Right? We call multiple integrals. We also call them iterated integrals. Right? Then I would integrate this over 0 to 6. And you say, well, wait a minute, this isn't any easier than the previous way. We still got to integrate this. Yeah, but now it's an integral containing only one variable, which means that I can go to my calculator. So the integral that was most challenging to handle has now been kind of taken out of the equation, so to speak. I never knew what soda and speaking had to do with one another, but. Okay, so I'll use X here instead of Y. And then slap on a dx here. And I get 275.01. You know, it didn't do me the courtesy of putting it into a nice fraction form in terms of pi. If I knew to be on the lookout for something in terms of pi, then I would make that conversion if necessary. But I can at least use it to verify. You know, I can do 864, feels right. 864 divided by pi gives you the same number. So no matter what the perspective is, it's still the same solid. So you would expect to have the same volume. All right. So no matter which approach you take, right? What this tells us is it's a lead into Coubini's theorem, tells us the order of integration is interchangeable, provided that the integration, the boundaries of integration follow a rectangular path or a rectangular model, right? So we'll have to talk about that more as we go forward, because it isn't always the case that the bounds are rectangular. You see in the second example, it's going from -1 to 1, -1 to 1, that's rectangular. But if I said go from -1 to 1, and then for y, I said go from -1 to, let's say, x squared, you know, some sort of variable set of bounds, that's a different story, right? And it's a bridge that we have to cross as we go forward. But that's where we're going to leave it for tonight. So let me stop the recording